Internal loads develop in structural elements. Before determining the properties of a structural element, it is necessary to know the force and moment acting within it. This chapter will present methods for finding these loads at specific points along the axis of element and graphically displaying their variation using shear force and bending moment diagrams. The applications will be shown for both beams and frames. Shear force and bending moment functions. In a provided image, a 30 beam is shown. A 30-foot beam is shown with components of forces R RAX, RRG, and downward force of 15, 15 kilos along the x-axis. A distributed load of 2.4 kilos per foot across the entire beam and an upward component RBG. The first step to solve this beam is to draw the corresponding free body diagram. The centroid of the distributed load in located by multiplying the base by height as it forms a rectangle. Similarly, the centroid for each rectangle is located at midpoint. Next, we proceed with the summation of moments at A, as it is a fixed support and has both an X and G components. The moment caused by the 15 kilos is negative and is multiplied by its perpendicular distance of 3.5 feet. The moment obtained from the centroid, which is 72 kilos, is also negative and is multiplied by 15 feet. Finally, the RBG components created a positive moment and is multiplied by 30 feet. All of these equals 0. Solving the equation for the unknowns reveals that RBG is equal to 30, 37.75 kilos. Next, we perform the summations of forces in the G direction. RGG is positive. The 15 kilos and 72 kilos are negative, and the RBG value of 33.75 kilos is positive. All of these equals 0. Simplify, Simplifying the equation and performing basic arithmetic operations, we find that RIG is equal of 49.25 kilos. Now, we move on the summation of forces in the x direction. The only force in this direction is RAX, which is equal to 0. Therefore, RAX is automatically determined to be 0. The next, we proceed to draw and interpret the shear force diagrams. The first diagram states that the force at AG, which is 49.25 kilos, is reduced by the product of the base multiplied by the height with respect to 30.5 feet and 2.4 kilos per foot. This gives a value of 8.4, subtracting this from 49.25 leaves of a value of 40.85, which decreases with an incline to the distributed load, reaching 3.5 feet. Next, the downward force of 15 kilos is subtracted from 40.85, resulting in 25.85. Then 25.85 is reduced by the product of the base multiplied by the height of 26.5 feet and 4.4 kilos, 2.4 kilos per foot, resulting in 63.6. This gives a value of minus 37.75, which also decreases with an incline due to the distributed load. Finally, the negative value of 37.75 is added of the positive RBG value of 37.75, resulting in 0. Now let's move on the last diagram, which stated that the sum of the larger base of the smaller base of the multiplicative be a certain distance and divided by 2. Here it's as follows: 40, 49.25 more 40.85 equals 90.1, and this is multiplied by 3.5, which represents the limit of another load that gives a value of 315.35, which is then divided by 2, resulting in 157 and 68. Then the same formula is applied again. 25.85 minus 37.75, which gives a value of minus 11.9. Now this is multiplied by 26.5, resulting in minus 315.35, and then divided by 2, giving a value of minus 157.68, adding this to the previous value yields 0. Thus, this verifies that the loads on this beam have been correctly distributed and specifically identifies the points where they carry the most weight. Translation. Then the same formula is applied again. 25.85 minus 37.75 75, which gives a value of minus 11.9. Now this is multiplied by 26.5, resulting in minus 315.35, and then divided by 2, giving a value of minus 157.68. In this to the previous value yields 0. This confirms that the loads on this beam have been properly distributed and specifically interferes the points where there bear the most weight.